Here are a couple more example problems involving lines and planes in R3. So here's a good problem. Let's find the line common to these two planes. So I'm giving you the equation of two planes, and I'd like to know the equation for the line that is intersecting both of these planes. So I drew a picture here. Here's a depiction of two different planes, and then there's a line in the middle. I want that line. So here is my answer. Well, remember, to find the equation of a line, you need two things. You need a point on the line, and you need a parallel vector to the line. So the first thing I need to do is find a point on the line. Now, a point on the line is any xyz coordinate that satisfies both equation 1 and equation 2 at the same time. So you could eyeball this even. You could just randomly guess and check values for x, y, and z that make both equations true. Well, I could see that there's a y in this equation and no y in this second equation. So why don't I just take y to equal 1 and x and z to be 0? That would be one point that satisfies both equations. So I'm going to pick my point to be 0, 1, 0. There, now I have a point on the line. Next, I need a parallel vector to the line. So let's look at this picture over here. I have two planes. Planes are described by a point on the plane and a perpendicular vector. So let's say I have this vector perpendicular to the diagonal plane I have here, and I have a second vector that's perpendicular to the second plane. If I take a cross product of these two vectors, I'll get a third vector that's perpendicular to the first two. And if you think about it for a moment, if I take the cross product, I'll get a vector that's parallel to the line. So my idea to get a parallel vector is to find a vector that's perpendicular to the first plane, find a vector that's perpendicular to the second plane, and then take the cross product to get a third vector that's actually parallel to my line. Well, I remember how to find planes, and when we found planes, we took a dot product. So recall, I'll write it over here. The equation of a plane looks like x minus a, y minus b, z minus c, dotted with a vector v1, v2, v3 equaling 0. So this vector v1, v2, v3, that's my perpendicular vector that's straight out of the plane, and a, b, c is a point in the plane. If you actually calculate the dot product, you're going to do v1 times x1. So you're going to get v1 x1. You're going to get v2 times v1 times x plus v2 times y plus v3 times z plus some other constant. I'll just call it d. But the constant d would be negative a times v1 minus b times v2 minus c times v3. I didn't feel like writing that down, but you get some other constant at the end here. My point is the coefficient in front of x, y, and z gives you your perpendicular vector to the plane. So in this plane, for example, the coefficients of x, y, and z are 1, 1, and 1. That is my perpendicular vector to the first plane. So my perpendicular vector to my first plane is 1, 1, 1. So this is perpendicular to the plane x plus y plus z equals 1. And I'm going to cross that with a perpendicular vector to my second plane. Looking at the coefficients of x, y, and z, I could see I have 2, 0, and negative 1. So this is perpendicular to my second plane, 2x minus z equals 0. Okay, so now I'll take the cross product. You calculate the cross product in this way, ijk hat. The first vector is 1, 1, 1. The second vector is 2, 0, negative 1. So calculating the cross product, the coefficient in front of I hat looks to be negative 1. So I have negative I hat. The coefficient in front of j hat, remember there's an extra negative sign in the definition of the cross product. So it looks like I get negative 1 minus 2, so negative 3 I hat, or j hat. And then the coefficient of k looks to be negative 2. So my vector is the vector negative 1, positive 3, and negative 2. Now, if you're ever worried that you made a mistake in calculating the cross product, you could always do a quick check. Take the dot product of your result with your two original vectors, and you should get 0 each time. And I could see that if I take the dot product with 1, 1, 1, I indeed get 0. If I take the dot product with 2, 0, negative 1, I indeed get 0. So now I'm ready to write down the parametric equations for my line. I have my point, I have my parallel vector. So the line is described in vector form as the vector 0, 1, 0 plus any multiple of the parallel vector, negative 1, 3, negative 2. So the parametric equations for my line are my equations. The x-coordinate is equal to 0 minus t. The y-coordinate is 1 plus 3t. And the z-coordinate is 0 minus 2t. And again, t could be any real number. These are the parametric equations for my line. I'd like to do another example, this time finding a plane. So which plane contains the two lines x equals 4 plus 4t, y equals negative t, and z equals 1 minus t. There's line 1. And I'd like to write down a second line. Now I already used the parameter t in my problem, so I'm going to use another parameter s. So I'll say x is equal to 4, y is equal to negative 3s, and z is equal to 1 plus 2s. I didn't want to use the same variable twice because I didn't want to imply erroneously that the t's in both equations have to be the same. These are just the parametric equations for two different lines. Okay, the question, which plane contains both lines? Okay, whenever you have a problem where you have to find the line or a plane, you first step back and think, what am I looking for? What do I need to describe a line or a plane? Well, in the case of a plane, you need a point on the plane and you need a vector that's perpendicular to the plane. So you need a point and a perpendicular vector. So here's my answer. So a point on the plane, well, the plane contains the lines that you see here. So if you pick any value of t, you get a point on the plane. So I'll pick t equals 0 here and find the point 4, 0, 1. So there's a point on my plane, but there's a lot of them. There's a lot of points on my plane. Okay, now I need a perpendicular vector to my plane, a perpendicular vector. Now to get a perpendicular vector, I'm going to again take a cross product. This time, I can look at the coefficients of t. I could look at what's in front of the t here, and the coefficients in front of t, 4, -1, -1, give me a parallel vector to my line. The coefficients of s here look to be 0, -3, 2. That's a vector that's parallel to this s line. So those two vectors are parallel to the line. Therefore, those two vectors are parallel to the plane. If I'd like a third vector that's perpendicular to the plane, I could take the cross product of these two vectors that are parallel to the plane. So the perpendicular vector will be the cross product of 4, -1, -1, with 0, -3, 2. So another calculation of the cross product, ijk. I'd put 4, -1, -1 here, 0, -3, 2. So the coefficient of I hat would be -2 minus 3, -5i. There's an extra negative sign on the coefficient of j hat when you calculate the cross product. I think it would be -8j hat. And then lastly, the k hat coefficient looks to be -12, -12. So my cross product has result 5, -5, -8, -12. Okay. Now, if you're ever worried that you did the cross product incorrectly, again, you could always check by taking the dot product and seeing that you got the right thing. But I think I got the right answer. Okay, so what is my plane? My plane is this. X minus 4, y minus 0, z minus 1. I got these numbers from looking at the point on my plane. And I'm going to dot that with the vector -5, -8, -12. That should equal 0. So I think I'm going to stop here, but if you wanted to, you can expand everything out and get an equation of a plane that looks like this. But we've done all the grunt work here. All right, fantastic.